All right, welcome everyone. Today we are also welcoming another rising star in the Institute. Tom Manzini is a PhD student in the Computer Science and Engineering Department at Texas A&M University. And if you haven't heard of his work, you certainly will soon. He's working as part of Robin Murphy's group and also as a CMU alum. He has a master's degree in language technologies from LTI here at CMU. So we're welcoming him back as well. And his talk today is on computer vision in drones for disasters. So please join me in welcoming our speaker, Tom.
All right, hi everybody. So as Norm so graciously introduced me, my name's Tom. I'm a PhD student and my work focuses on computer vision. Specifically building computer vision systems that can go across sensors and across sources. We're going to be talking today about applying this work and exploring this work in the disaster response setting. And so with that, let's get into it. So when a disaster happens, there's a bunch of unknowns that creep up. Nobody quite knows where the damage is, or where the bad stuff is. There's a big need for information. And so to try and fill that gap, practitioners, emergency managers in the field, they deploy drones, they deploy crewed aircraft, and they also deploy satellites. And the purpose of these deployments is to get as much information, as much imagery about the scene as possible. And then humans take that imagery, they make decisions with it. They're looking at these destroyed buildings, destroyed roads, piles of debris, trying to say, where's the bad stuff? How do we get there? So this problem has been known about in the computer vision community for a while, but the computer vision community has really started to try and tackle this problem from a bunch of different angles. So coming out of the remote sensing community, there's XPD, there's the Bright data set, IWD, there's a bunch of others that all try and look at satellite imagery and come up with labels for what's going on in that imagery in hopes of supporting disaster response. Out of the crewed aviation sort of academic community, and also just general disaster response, we've got the LADI dataset series, and we've got the Volan dataset series. And then coming out of the robotics discipline, we've got a bunch of data sets, the ISBITA, Adder, FloodNet, RescueNet, and more. But the problem is that there's a bunch of duplication of work here. The same task is being explored across a bunch of different sensors, primarily because of the divisions that have that have crept up within academia. Remote sensing doesn't always talk to computer vision, doesn't always talk to robotics. There's a bunch of spread out efforts. And so, my work is trying to bring these together. Now, another reason why these things have been spread out across these different disciplines is that in practice, decision makers are using different sources at different rates. Some places prefer satellite imagery, in some cases, but that's also a problem because satellites can be out of position. They can be tasked elsewhere. They're a strategic resource up in space, so there's not very many of them, and people need to be choosy about where they get sent. Also, some satellites can be obscured by weather. There's some that can't, or that can see through some of the weather, but it's not always a fair expectation that your satellite's going to be ready to go whenever the disaster happens. Flip side, crewed aircraft, weather, high winds, a lot of these major disasters are caused by weather events. So getting crewed aircraft into the scene is sometimes a difficult task. And at the same time, there may be operations going on in the disaster scene that prevent or limit the use of crewed aircraft. It can be risky to put a person in an airplane over a disaster scene when there's a bunch of things going on. And then lastly, for drones, high winds may prevent the flight. Crewed aircraft traffic in the scene may cause drone flights to be risky and then pushed off. And the teams themselves are strategic resources, so you need to be choosy about where the drone teams get sent. What this means is that in practice, you don't know when you go to a disaster what sort of imagery you're going to be getting. The scales that you could be getting could come from space. They could come from a couple hundred feet above the disaster scene. And at the same time, you don't know what sources are going to be available because who knows whether or not the drones are going to be flying, the satellites are going to be visible, the satellites can see the scene, I'll say. And so when it comes time to build these computer vision systems, models, we need to build models that are able to leverage whatever type of imagery happens to be available at the moment, as opposed to building our systems to deal with the the niche drone imagery or the satellite imagery or something like that. Now, this is kind of what the talk is going to be about. This is sort of my effort to try and build that bridge between these disparate sources. And the way that I'm going to be talking about it today is through this metric that we have for this imagery called ground sampling distance. Now, this is a measure that sort of lays up the imagery that's been collected on the surface of the Earth and then measures how big the pixels are with respect to the actual space that they're imaging. So satellites, going to be somewhere, and for disaster response applications, there are a bunch of different satellites, but for disaster response applications, you're going to try and get as high resolution as possible, and that's going to put you sort of broad strokes in the 30 centimeters per pixel range. So about this big, maybe this big for a single pixel. For crewed aircraft, you can choose the altitude that crewed aircraft flies at, but you're going to be somewhere around 9 centimeters and usually a little bit more than that. So 9 centimeters per pixel. And then drones can really get as close as you want, before you start worrying about colliding with the object. So it's very common to see 3 centimeters per pixel, but it's you should expect this type of imagery to be operating at the sort of 9 centimeters per pixel there. This spatial data, or the spatial grid that we're going to be talking about today, represents sort of a scaffolding that we can use to bridge these different scales. We're going to be talking more about that in a moment. So I guess with that, I should probably call out that this is not just a problem in disaster response. This is a pretty foundational problem that bridges a lot of different disciplines. Medical imaging, when a patient comes into a trauma center, a bunch of scans get ordered all at the same time. They can get sent for MRI, CAT scan, they can get labs pulled, or x-rays as well. And a lot of this imagery that's collected for medical patients also have this spatial property, also have this disparate source property. Same thing is coming up with microscopy. You could have a sample that you want to image with a bunch of different microscopes. Those microscopes are going to have different spatial resolutions as well. Astrophotography, different telescopes, different resolutions, different fields of view, same properties come up. And also in meteorology, a lot of the modeling systems that have been developed are operating on sort of voxels. And so those voxels have spatial resolutions as well, sort of kilometers per pixel or meters per pixel in the case of really niche models. And so what this means is that if we are able to tackle this problem in disaster response, then we can have a bunch of impact in all these disparate fields, in all these other fields as well. And that's because these problems are really isomorphic. Like, if this property of spatial imagery is something that spans a lot of different disciplines. So we're going to be talking again about this through the lens of disaster response. And as I kind of mentioned at the beginning, when a disaster happens, emergency managers, disaster practitioners look at this imagery in hopes of answering two main questions. There are a bunch of sub questions, but these are the main things that people care about. Sort of, where's the bad stuff? Where's the damage? And we're going to be looking at that for buildings. And then where is sort of, how do we get there? And so we're going to be looking at that for roads. The vast majority of this conversation today is going to be focused around building damage because that's probably the most mature effort in the academic realms and also in our efforts. But there's also some interesting work that we're doing on roads. And so not going to have too much time to talk about it, but I'll have some slides that call out to it. So topics for today. We're in the process of building these systems that we're trying to build them so that they can go across these different scales and sources. And a huge portion of this has been collecting and curating the data necessary to sort of make that happen. So that's going to be the first thing that we're going to talk about. We're going to talk about some of the early results, some instances of what would otherwise be really performant models falling flat on their face when presented with disparate source imagery. And then the thing I'm really excited to talk about is that as a sort of byproduct of this work, we had the chance to deploy these models operationally as a part of the multi-agency responses to Hurricanes Helene and Debbie in Florida and also in Pennsylvania. And so we've got a couple of I'll say a couple of learnings to talk about, but a bunch of learnings behind the scenes that are also worthwhile. And then a little bit of a discussion on future work, the things that we're actively working on, that didn't get a chance to be included too deeply in this talk. So let's talk about data. So for those of you who were here for my talk last year, we presented the CRASAR UDroids dataset. This is a dataset at the time that was only uncrewed aerial imagery, these UAS drones that are flying, that were flying at 10 major disasters. It was 52 orthomosaics, 21,000 and change building polygons. All of these buildings were labeled for their damage classes and were also labeled for spatial alignment, kind of a registration problem that happens in the imagery. We're going to be talking more on that later. It's 68 square kilometers and it's 67 gigapixels. So these are really high resolution images. On average, we're in that 3 centimeters per pixel ground sampling distance range. Most of the imagery is captured from the American South, but we've also got the Mayfield, Kentucky tornado and Kilauea volcano eruption. So it's a good, it's at the time and still today, it's the largest and most diverse drone disaster imagery data set available. And I'm excited to say today that we've had the chance to expand on it. So since we released the CRACE RU droids dataset, we have also gone out and collected parallel satellite and crewed aircraft imagery for the same scenes. This means that we can, I'll just go through the stats. We've got 3 sources now: satellite, crewed, and the original drone imagery. 265 orthomosaics. We're up to 122,000 building polygons. So it's 122,000 labeled examples in the data set. 70 gigapixels. You notice it doesn't go up very much because that drone imagery is super high resolution, makes a huge portion of the data set. Crewed imagery, satellite imagery, lower resolution. What you will notice, though, is that the area has not changed. That's because the area that was imaged is the same. So we can go to the same building captured from all of these different sources. So it's parallel. So parallel data from satellite, crewed aircraft, and also from drones. We've got the same building being imaged across all these different sensors. And so what that means is we have the example. This is an example. So we've got the drone orthomosaic that we presented earlier with, or last year with the CRACE RU droids data set. But we now have additionally the crewed aircraft. So in this case, this was a NOAA overflight of Fort Myers Beach following Hurricane Ian. Then we also have the satellite aerial imagery collected in this case from Maxar. So we have parallel data, and this means that we can, zoom in, look at the imagery, and start to make judgments about it. So this is an example of what the labels for building damage look like. We've got these building polygons, which are given to us a priori. So one of the quirks about this data set is that it aligns with operational practice. And so in practice, emergency managers will decide on a set of building polygons to use during the response. And so we use those polygons. This is not a question of trying to detect where the buildings are. We've got the buildings already. We need to go and label them. So that's what this imagery looks like in practice. But we can now go and say, hey, we got this one building that we're really interested in. Let's look at the combined view between the crewed aircraft, the satellite imagery, and the drone imagery. And you can tell there's a lot of noise in some of this imagery. Like I said, the satellite imagery is captured at around 30 centimeters per pixel, but we have the high altitude aerial imagery captured by NOAA in this case at 15 centimeters, and then Florida UAS-1, the UAS task force that was deployed to Fort Myers following Hurricane Ian, captured this imagery at around 3.1 centimeters per pixel. So we've got the same scene being imaged now from all these different sensors. This is starting to look like what practitioners actually see in practice, but at the end of the event. In reality, imagery arrives sort of as a dripping faucet. A little bit more on that later too. And so, as I said, we've labeled all of these buildings across all of these sources. So we're up to 122,000 and change labeled examples. And each building, each image, has its own label. That's given us an interesting finding, which I'll get to in a moment. The labeling system that we used was, yeah.
There's a question. You said you have the building coordinates. How did you get that?
So the question for those online was, we have the building coordinates, we have the building polygons. How did we get them? Those were given. So in practice, those are decided upon at the start of the event, at the start of the disaster. So counties maintain building polygons in some cases. OpenStreetMap, Microsoft Bing Maps maintain those publicly as well. And so when a disaster happens, practitioners kind of say like, hey, the most recent one came from Google or came from our county. And so they pick that one. In our case, the actual source was all Microsoft Bing Maps because that was the most recent data that we had for the different sources. The labeling schema that we used for this data set was the joint damage scale. This is a schema that was developed in conjunction with, developed for satellite imagery for the XBD data set. And we chose this labeling schema because we knew at the start of the project we wanted to go across scales. And so we believe that choosing a schema that was one, dedicated for aerial imagery. It's the only data set that's, the only labeling schema that is designed specifically for aerial imagery. But also one that was already in use by practitioners for satellite imagery would mean that we could, at the very least, trust the labeling schema to work with aerial imagery and trust it to work with practitioners. So that's why we went with it. Now, as I mentioned earlier, all 122 building polygon labels are unique. So we've had an annotator and then a bunch of, actually several reviewers look at each building polygon and each piece of imagery and say, this label's correct. And it's, again, not unique per building polygon, it's unique per image. So that means that in these 3 images, there are 3 unique labels that were each reviewed several times and generated by different annotators. What this means is that, what this means, well, this feature of our data set has led us to 2 big findings, or 2 main findings. The first is that the labels that are generated by annotators and then by reviewers vary a lot with resolution. So what this means practically is that when you show the same building to different annotators and review it and curate it, the people who look at the satellite imagery are going to underreport damage by about 20%. And when it comes time to train machine learning models, this means, well, there are a bunch of implications, but for machine learning models, you can't just resize your image because if, the standard practice that's taken when you're dealing with these, weird sizes, weird spatial resolutions is to just say, all right, everything's going to be like 640 by 640 pixels, and we're just going to call it a day. If you do that in this case, you're going to be losing about 20% of your damage, or underreporting damage by about 20%. And this is a pretty pervasive problem. Here are just a bunch of examples that we included in a fact paper on this topic earlier this year. But if you have an annotator look at the building in the bottom left, building 1, a satellite view, they label it very consistently as minor damage. You show the same building image from a drone to a different annotator, they label it very consistently as major damage. This trend is very consistent and goes throughout a bunch of different disasters. So we evaluated this at Hurricanes Ian, Hurricane Michael, and Hurricane Harvey, found the same trend. Here's the upshot. Don't worry about the different gray columns, but just look at the difference between the black column and one of the gray columns. That's satellite versus drone. So in the drone, so in this case, drone imagery classifies significantly fewer fewer buildings as no damage. So what this means is that you send a drone to the same spot as you sent a satellite, you compare the two are going to get different answers and very, very tiny p-value. You're going to be catching a lot more of that minor damage with drone imagery as well, more of that major damage, but it looks like the 2 sources are about the same when it comes to detecting destroyed buildings. Now, what this means, I'm sure you can see the operation or the implications for modeling. If you can't just throw all of your imagery into one bucket, train it on a bunch of different labels and expect a good output, because the underlying distributions themselves are different. And so we need to be a little bit more conscientious about it.
What are the error bars on each one of these? Like how variable is it within them?
So we didn't do error bars, we did p-values. So very tight p-values. So like p to the minus 75, 67, and 117.
So that is between the drone versus, like, let's say not any of the ones, right?
Yeah, exactly. So the statistical test here is what's the probability that these 2 distributions are the same, and so that's the p-value for it. So we're willing to hang our hat on those p-values. And if you guys are interested in this result, you guys can go to the ACM fact paper that we published on it. The citation is there at the bottom. Now, what this means from a modeling perspective, as I mentioned, you can't just throw all your data into a bucket and train on it. The underlying distributions themselves are different, and so we need to be a little bit more conscientious about how we handle it moving forward. The second thing to mention is that this finding shows us that we don't know what is actually happening on the ground, because these 2 distributions are statistically different, very significantly so, and one of them has to be wrong. I can't tell you which one. We don't have ground level data to actually go out and say, hey, the drone is closer or the satellite is closer. But the conditions that are being reflected by one of these is going to misrepresent the actual conditions in practice. Yeah.
Tom, there's a question in the chat. I think you have it up there. Maybe you could just read it out and answer it.
The question is, in the Cresar Udroids dataset, did you create true orthorectified imagery, parentheses, geospatially corrected with geometric and terrain distortions removed, or did you create georectified / georeferenced imagery only? So we did not account for terrain distortions in the Cresar Udroids dataset. The reasoning for that is because in practice during disasters, usually that type of additional processing doesn't happen. And so we wanted the imagery to be as faithful to practice as possible. And so what we're getting is really an orthomosaic of these images tiled together, kind of laid up on top of each other. And those are then georeferenced. The explicit process by which we got to that imagery, you can find in the Cresar Udroids paper, which is up on archive, and I can send you a link, Matt, if you're interested. Cool. So one of these distributions has to be wrong. We don't know which one, but this also has not just implications for how we train machine learning models, but how we also communicate the products of the models to disaster practitioners when it comes time to actually ship them out. Yeah.
My understanding is that the satellite photos, I think, were more fuzzy than the drone ones.
Yeah.
If you ever looked to see if you made the drone ones fuzzy, if people would also underreport the damage in the same way?
We have not done that. So the only comparison that we've done for this line of work is just full res drone, full res satellite. We haven't augmented them in any way because we wanted to align with what practitioners would see in the field, kind of get as close to that problem as possible. Our intuition, I should say, is that the resolutions are the thing that's driving this disagreement. But it could be like some dynamic specific to satellite or specific to drone imagery that's causing this as well.
Yeah, because I feel like the higher resolution would indicate there's more information and better.
Yeah, that's our intuition as well. The more information you have about the scene, the more likely you are to spot that fine damage that you wouldn't see in a low res image. But at least I'll say in the disaster response literature, because these different academic groups, remote sensing, robotics, crewed aircraft imagery, they've all been operating in their own world. They've all been reporting, hey, we can give you an accurate picture of your scene based on this imagery. And this is the first piece of evidence that I've seen, at least, that gives some contradiction there, saying, hey, there's a big difference between imagery-derived labels and what people actually see on the ground. That's some intuition that practitioners have had, but this is the first time we actually have numbers to back that up. The second finding that we've had, aside from this label disagreement across sources, is this issue of, we're calling it spatial misalignment. For those of you in the computer vision community, it may be closer to image registration, or the real techie term is cadastral registration. But the problem is basically, when you take a bunch of images, you stitch them together in this noisy way that's done in practice, you get a bunch of distortions that creep into your data. And that means that the locations of the building polygons that you have are going to be slightly off of the locations of the imagery that you get. Now, this is just an example so you can see, it's not a very obvious, difference, but there's definitely shifting going on here. The building polygons are not actually in the exact same spot, despite the latitudes and longitudes being the same for at least this collection of imagery. And there are a bunch of reasons why this is caused in practice. The drone, the satellite, the crewed aircraft that's collecting the imagery could be having some GPS noise in its sensor. The process by which these polygons are generated is almost exclusively looking at a satellite image or looking at a crewed aircraft image and then segmenting the polygon, or segmenting the building out and generating a polygon from that. So that could be a segmentation error or like a polygonization error. And then the last thing, which is the one that I alluded to earlier, which is that when you're actually taking all these images that are captured by these different sensors and stitching them together and laying them up on the surface of the Earth, there could be some errors in that process. So there are a bunch of reasons why this can be caused, but the important thing is that it's there. And I think interesting thing for the purposes of this talk is that it's a pretty substantial issue, especially in UAS imagery, which is the worst case. So there are two charts here. The chart on the left is the intersection over union of the building polygon where it belongs in the imagery and then the uncorrected building polygon. And we see that at the median, it's around 0.68. So we're losing about a third of the building. For models that we train, this means that if these things aren't lining up with one another, then the building polygons, the models are going to miss about a third of the area that each building polygon is is trying to capture. So if there's damage outside that building polygon, models may miss it. And the flip side is not just measuring in terms of IOU, but also in terms of pixels. We're off by about 75 pixels. This doesn't seem like a lot in drone imagery, but it corresponds to this 68 IOU. So for training models, we want to correct this issue, and we want to do this for two reasons. One, we want to actually reduce the noise that's present in the labels that are generated both during training and inference, but also as we look towards training these multi-source models and eventually models that can consume more than one view of the scene at once. Then we need these images to line up. And so to do that, the Cracer Udroids dataset also has spatial alignment labels for all 122,000 building polygons. So this is a linear translation that takes a building polygon and shifts it into position. And the way that we've done this is by learning templator by providing vector fields that adjust the locations of the building polygons into position on top of the reference imagery. Now, this is the reason why we're doing this, as I mentioned, is that it leads to biases during training and errors during inference. So on the far left, this is an input image that we've given one of our trained models. In the middle, we take the building polygons that are misaligned, drop them on top, and tell the model label it. And you can see some parts here cropping up in purple. That's the model saying, that part of the building doesn't belong to a building. So we're going to have errors in our modeling process crop in if we don't correct for it. So those are, I think, the main findings from just the data set development part. I'm starting to talk about models here, so we're gonna jump in some early results soon. But the Cracer Udroids data set, at least not just the sole source UAS data, but now with the 3 crewed satellite and drone imagery, represents the only data set of its kind, at least that I'm aware of, that has all 3 of these sources parallel and labeled independently. And so we think it's going to be a platform for being able to train these multi-source models. So let's talk about some early results. So we got a latex table here. I'm not going to spend too much time on it, but the main thing to mention is we've trained a bunch of different model architectures on this data in hopes of getting good performance. It's interesting to see here that the hot architectures are not doing so well on this task, and our best performance is coming out of just a vanilla unit with attention. Or excuse me, not vanilla, but a unit with attention, giving us a macro F1 score of 0.55 when we deal with that spatial alignment issue, or 0.52 when we don't. This has been a big effort to get these models in here to try and increase performance. There are a bunch of reasons why I think performance on these large scale models that typically would perform good elsewhere aren't performing very well here. But I think that's a conversation for another time. The next thing that we've done, I guess the thing to notice, we leave about 3 points of macro F1 on the table by not dealing with spatial alignment. Disaster response is a setting where you really want to be hunting for as much performance as you can, and so this is something that we've looked at correcting. And so I'm going to take a brief diversion here just to talk about spatial alignment. Some of the models that we're training, this work is still in progress, but I think it's fun. So we have the process that we've built right now is just looking at buildings, coming up with labels. But if we train models to actually deal with that spatial misalignment, can we recover any of that macro F1? And the answer is that yes, we can. If we train cadastral registration models to try and pull in those building polygons on top of the building, those building polygons on top of the buildings, we can get about a little bit under half of that performance back. So we're able to deal with some of that in practice, but it's still there's a lot to go. Now, I hear you guys thinking, I've spent all this time talking about crewed and satellite data. What's going on there? So we've got the UAS baselines. That's where we've spent the vast majority of our time up until now. We're starting now to train these crewed and satellite models as well to see how well they perform going across scales. Now, the way that we've done this, these are just some early results, but the way that we've done this is we are taking the top performing baseline that we have, this unit with attention. And we're going to be training it on the different sources and testing it on the different sources, kind of seeing how it performs across source. And this is, I know it's a confusion matrix, but this is what we're seeing. So if you take a model trained on drone and test it on drone, you get that 0.554 number that I was showing you on the earlier slide. But if you take that same drone model, test it on crewed aircraft, you lose about half the performance. You test it on satellite, you lose even more performance. So that's the top row there. If you train a model on crewed imagery, it's clearly like a harder task to learn, but you see performance drops going off on both sides as you go to higher resolution imagery in satellite imagery, in drone imagery, and also lower resolution imagery in satellite. And then the same goes for satellite. You lose a lot of performance. Again, just going from satellite to crewed with about 0.4 macro f1. You lose about half of that performance going to crewed, and then even more of that going to drone. So this is a tough problem. It's not, even if you throw in all this data that we've collected, it's still a tough problem. Now, the last row and the last column is us doing the sort of standard fare of just let's throw it all into one big pile and train on it and see how we do. So, I mean, we do get a little bit better performance across each one of those sources, but never as good as the individual models that are trained for that specific source. So we're going to be over the next few months, we're going to be really optimizing on trying to improve these different models on these different sources. So we finally got the data to at least measure it. We've got the data to train on it. And I'm going to talk to you now about sort of what we're going to do to try and improve these models. This is work that is actively in progress right now. So if you've got thoughts about it, please come and talk to me. I'd love to hear it. But the fundamental idea is that we're going to represent these images in the frequency space. So this notion of ground sample distance, the critical insight is that this is itself a measure of frequency. So centimeters, yeah.
Sorry, can I ask a question about the previous one? Do you have a sense for why the crude one is worse than the satellite? Like, does that have to do with the oblique?
Sorry, you mean why this one is worse than this one? Yeah, that's my intuition. Is there's less crude imagery in the data set as well, and so we think it's harder for the models to go from those fewer examples to new examples than the 0.39, which has a bit more imagery. So for context, for every crude image, there are 2 satellite images on average. And that's usually because satellites have been revisiting that same scene. So we just have more satellite data to train from. That's our intuition. So the thought is we have this, this scaffolding in this imagery. It's of ground sample distance. The insight here is that this is a measure of frequency, centimeters per pixel. It's a cycles per unit of time, cycles per some unit. And so we can leverage that explicitly if we operate in the frequency domain. And the thought is that decompose this imagery into its spectral components using a Fourier transform. Pad clip those frequency components so that they're to the same dimension, and then we train those models on the spectrograms directly as opposed to the pixels. And so we've got the same scene here being represented at different ground sampling distances, but different spectrogram. But the underlying frequencies are still the same, at least in the lower frequencies of this image.
Another question from Matt in the chat.
Matt, for the lower F1 performance, do you think that the reduction in performance is due to misregistration from model training or another reason? So in the cross source training, I'll just go back to this. So in this chart, all models were trained on aligned building polygons. So we took the effort to make sure that all building polygons were in the right position during training. The main issue that we think for the reduction in model performance going across sources, we think it's primarily due to 2 factors. One being the variations in variations in the spatial component of the imagery, but also there are a little bit of different dynamics in the imagery itself. So for example, satellite and crewed imagery have a little bit more of a chance to view buildings from their sides, like a slightly oblique view, whereas drones tend to have that opportunity or tend to not have that property as much. So there are some sensor specific dynamics there, but we think the majority of the performance reduction is due to variations in scale. So the thought is, in this setting, when we're working with the spectrograms, the same low frequency components correspond across all of these images. The only difference is the high frequency components, and as a result, if in this context, when we're training on the low resolution imagery, zero frequencies in the high zero values of zero in the high frequency data actually corresponds to actually has meaning as opposed to just padding your imagery or rescaling your imagery, which can create aliasing and have a bunch of problems. There are some really interesting properties to these representations that we're training that we've found as we've trained them. The critical thing here is that the data generators that you're using to feed your models have to be the same spatial dimension, not the same pixel dimension. So for this work, gone are the days of 640 by 640 pixels or 1024 by 1024 pixels as your inputs. You now need to sample at 50 feet by 50 feet or 100 or 70 meters by 70 meters. That way, the frequencies that you're seeing in your spectrograms and the models see over time are the same wavelength. And so the models are able to learn consistent kernels. And that leads us to this property of scale invariance. And falling out of that are some really interesting things that happen. The first is that you can encode the ground sample distance properties directly into the learned representations. And the second is that as you pad and clip these representations, you can trim the high frequency data from your imagery's representation by operating in this spectral space. And then finally, the thing we're looking at right now is that these representations can be used directly as inputs to state space models that are operating in the frequency space as well. So there's some really cool lineage here. All right, that concludes the sort of early results and what we're. Oh yeah.
So why not then do actually wavelets? Because you also have localization that seems like that's going on there, right? Especially, I don't know, you went to a road mod.
Yeah.
Like road image here, but in the building case, there's localization and maybe high frequency because something is down and something is not. So would that maybe work better than just doing global frequency?
I'm sorry, you said wavelets?
Wavelets,
yeah. So one of the reasons why we're interested in global frequencies is that these drone images are very high resolution, and so they need and so to actually label them effectively, we think that we need models with very high receptive fields. And so that's why we're gravitating towards global kernels and frequency-based representations as opposed to wavelets. But I think there's gains to be made on both fronts.
I had a question. Sorry.
Yeah.
What's your thoughts or intuition behind if you get multiple resolutions, zoomed in, zoomed out, blurred in? That's something I've seen people do when they're dealing with different resolutions.
Yeah.
They just add all of it in.
Yeah, I mean that kind of comes back to what I was saying or what I was showing earlier is this, if you just train on all of your sources, if you and this is a pixel data generator, we're just generating samples of 1024 by 1024 and feeding all those to the models. We're doing data augmentation in this as well. So we are trying to blur it and sort of generate data that has kind of got those properties as well. But we're still, I just think we can do better than this number. That's my intuition. All right, I promised you guys a little bit on this. We don't have too much time to talk about it, but one of the things that we've also done, so there's two tasks that practitioners care about. One is where's the bad stuff, and the other one is how do we get there. The how do we get there problem is really interesting. There's a bunch of cool problems around how do you build metrics for actually measuring damage in roads. To that end, we've also just released the RDA road damage assessment extension of the Cracer U-Droids dataset. This is only the drone component, but it's 657 kilometers of road, all labeled according to a custom schema that is practitioner relevant. We spent a lot of time interviewing people at FEMA and Texas Department of Transportation to make sure that these labels were worthwhile. And it's the same 67 gigapixels that you're familiar with from Cracer U-Droids, the drone portion, and the same area. So it's all parallel data. If any of you are interested in multitask learning, there's a bunch of cool problems in here that I can point you to. Just let me know. And it's going to be at AAAI this year or next year. All right. So with that, We've trained a bunch of models. We've got a bunch of data. One of the really cool things that we had a chance to do was actually deploy one of these models operationally as a part of the multi-agency response to Hurricanes Debby and Helene. This was a fairly substantial effort that covered both Florida and Pennsylvania. So excited to talk about that today. Before I do, I'm going to give you just a little bit of context on what goes on at disasters in terms of the drone response. And again, the reason why we're doing the drone response is because those are both the most performant models that we had. They're also the only models that we had at the time. We were also labeling in the background as this was happening. But let's jump into it. So the first thing to mention is that the deployment that we had occurred during the first 3 days of Hurricanes Debby and Helene. This is from Hurricane Ian, just to give you sort of a sense of what drone operations look like. So the first 4 days in this case were all reconnaissance. We're not flying drones in buildings, hunting for survivors. We're just trying to figure out, again, where is the bad stuff? Just doing reconnaissance. Only on days, what is that, 5 and 6, did we get into technical search and other stuff like that. So this was almost exclusively, the operations that we were involved in at Hurricanes Helene and Debby were exclusively reconnaissance, and that's consistent with past deployments. The other reason why we thought these drone models would be useful is that there is a huge wireless constraint that happens in practice. So when drone teams go out into the field, they very regularly saturate the wireless networks that are out there, making teams and other people unable to transmit imagery, and also for emergency managers to get the complete picture of what's going on. I love this chart. I'm going to walk through it just a little bit because it's worth sitting with. The blue vertical lines represent the gigabytes per hour collected by drone teams in the field. And the horizontal bars represent the upload speeds observed in the field, again in gigabytes per hour. So anytime one of those blue bars passes that horizontal line, teams have collected more data than can be uploaded. This isn't too big of a problem on days 1 and 2, but once teams transition to mapping, which is what the orthomosaics that I've been talking about are focusing on, this whole system breaks down. Like, you just have to be very selective about the data that you want to send, and so you end up shouting at people over a radio about what you see in the orthomosaics. It's a tough balance. This is one of the reasons why we went down this road for working with orthomosaics, is because there's such a problem to deal with in practice. And so the operational deployments that we worked with were exclusively orthomosaics. And we did building damage assessment and we did road damage assessment on both of those tasks for these images. So the pattern that we took. Oh yeah.
Yeah. So is there an advantage here to, like, the satellite data could actually maybe be downloaded earlier than?
Yeah, absolutely. So it's a really rich trade space here. The benefit is that so for satellites, for example, you're absolutely right. Satellites download their data to like high throughput internet connected, sometimes data centers, sometimes just dishes. But like they get connected to backbone internet speeds and can immediately get that data shipped to whoever cares about it. The flip side of that is that whoever needs to receive it also needs to be connected to the internet. And that's often a problem for practitioners in the field. It works great when you're like in an emergency operations center, but if you are in the disaster environment, it's hard to get satellite imagery to you. Airplanes have that same problem to a lesser degree. The data lands on the airplane and it lands at an airport. Sometimes there's good internet there, sometimes there's not. Drones, maximum extreme, they're operating in the wireless denied or wireless limited environment. And so there's a big balance there. So one of the reasons why we wanted to focus on drone imagery early on is because of this wireless limitation. We thought that if we could run models in the wireless denied environment, we could send the model outputs, which are typically smaller, over whatever wireless data happens to exist to practitioners, and then they would get the full imagery eventually. So that's this product is. So we take the imagery, we take these predefined spatial data products, buildings and roads, run them through a machine learning model. We generate these outputs. Usually these are like, for those of you who are familiar, these are like GeoJSONs or KML files that have the locations of the buildings and their labels attached to them, or the locations of the road and the labels attached to them. And the thought is we get these out the door first with the limited wireless we have, and then we ship the imagery that we're working with at the end of the day once we've got the bandwidth to do so. And usually this is physically like just putting the SDs in a car and driving it somewhere. Going through this cycle, getting the data products out the door first, we think can enable decision making about 1 day in advance. Typically, the full imagery arrives at the end of the day after teams have gone to, after sunset. We can't collect imagery anymore. People are going to sleep. So typically, it's one full operational cycle until people can actually look at that imagery that was collected the day before. Yeah.
Where's this inference typically actually happen?
That's a great question. Yeah. So for drone imagery, broad strokes can't happen on the cloud because it's not connected to there's no wireless. So the expectation is that this imagery or inference happens on compute that you bring into the field with you. It's not happening on the drone, but it's happening on like a desktop or like GPU laptop that you've got in the field with you. Does that answer your question?
Okay.
Yeah, I'll say that's the dream. That's where we're going. The 2 deployments that we were a part of, that happened. They not emailed, but they sent us the data. They sent us like links to the data. So we're in the process of tightening that cycle, but it involves us getting, having the connections to the practitioners to go into the field with them, having that trust. We think we're there with some of the teams in Florida, but it's a very individualized process because there's no centralization for these disaster response teams. They're it's different for every state, different for every city, and so you need to build that trust with the individuals you're going to be deploying with. Yeah. So we take this process, and again, we were comfortable with this because we thought we would be deploying these models only on high resolution imagery. We were thinking sort of less than 12 centimeters per pixel, keeping us pretty squarely in the drone imagery category. It turns out that wasn't the case, but we'll talk about why that happened. So let's now that we're done with the background, let's talk about the actual deployment. So we deployed twice for Hurricane Debbie, once in conjunction with the Florida UAS-1 task force as a part of Florida Department of Emergency Management. And the flights were done using a Wingter 1. And then the second one was in Pennsylvania with the Pennsylvania Emergency Management Agency. They were actually flying crewed aircraft. We were very explicit about the problems that we've encountered with spatial resolution, and they were very confident, and I think rightly so, that the pilot could fly at a low enough altitude to collect the imagery that we cared about at the resolutions that we cared about. Props to that pilot because he did do it, but it was definitely weird imagery to see from a crewed aircraft. And the second one we did was Hurricane Helene. This was a Category 4 hurricane that landed in Florida. Again, it was the same team that we have been deploying with, and so this was again with their Wingter 1 and again with FLUAS-1. We think this is the first deployment of an automated damage assessment system as a part of real-world operations. I keep saying this, and nobody's contradicted me yet. So if anybody has any other information, I'd love to hear about it. So again, we saw kind of what we've been talking about happen in practice. This is crewed aircraft imagery collected in Pennsylvania in Tioga County from PEMA's the Pennsylvania Emergency Management Agency's aircraft. Again, and we saw a bunch of model degradations happen with spatial alignment being varied. So you can see as the building polygons get moved off of the buildings, then it goes from as we would judge it, all correct labels on the left-hand side of the screen to only one correct label on the right-hand side of the screen. So there's definitely degradations here. At the time we didn't have models ready to pull back that misalignment, try and recover that additional performance. So it's I guess validating to see that the problems that we thought continue to exist in practice when we see them. But it was a challenge. We tried to manually correct these labels instead of having a model go in and tell us the translations. We did that in a couple places, but in a couple cases there was just too much imagery to go through on our timescales. So yeah, we did it for one orthomosaic at Beagle Beach in Florida. The other thing that we saw is that the variations in spatial resolution also degraded model performance. I don't have hard statistics for this because we haven't labeled this imagery yet to actually get us, what we would consider as ground truth. But the thing I want to call out is the ground sample distance column in this table up here. So this is what was transmitted to us. So Hurricane Helene, Beagle Beach, 25 centimeters per pixel. This is a drone orthomosaic. The reason why it's so low resolution is because they intentionally downsampled the imagery to ship it as quickly as possible over, again, the limited wireless networks. This is another signal that the models that we're building it doesn't just matter about source. It could be drone, but they could be doing weird sampling things just to get it to the practitioners. Mayo, Florida, and Brantford, Florida. Two other orthomosaics. Those were right in line with our expectations for ground sample distance. We ran those models and had, again, we haven't labeled them because we don't know the hard numbers about whether or not these models performed well. But I can tell you intuitively, these outputs look great. And then again for Tioga County, we had 9 to 11 centimeters per pixel, less than that 12 centimeter per pixel threshold that we set for ourselves. The pilots hit it, great on them, and we were able to run the models in practice. This is just an example of what the spatial resolution looks like. These these two images have the same pixel dimension, but you can see one is, one you can say, see individual roof tiles and bits of the ladder, whereas the other one you're looking at an entire building with just noise and debris. So for those of you who are machine learning people in the room, I'm sure you can understand that having a CNN that you've trained on one scale, trained to look at this image, go look at this image, it's gonna break. So this is the sort of problem that we're trying to deal with. The other thing to mention, this was one of the really big learnings for us. We had an intuition of this going into the deployments, but just a little bit more context here. The products that we delivered to the emergency managers matter a lot. So it's great that we're able to run the models, but if the practitioners can't interpret the outputs of those models in a way that makes sense to them, the whole thing breaks down. Like there's just a block there. So we initially went into things saying we're going to give you an orthomosaic with the building polygons and road lines on top of them, like statistics of like this area's got this many destroyed buildings, this area's got a different count. And then we also gave GeoJSON and polygon files. Point and polygon files. And so it looked like this sort of, these were the products that we were giving to them. And we got a message basically saying, hey, this is great. I can't open any of these on my phone. So we need it as a spreadsheet. So we updated it to give all these products also as just a CSV that practitioners could open in the field on their phone, and then also as a PDF and PowerPoint file that they could again open in the field on their phone. So if you're gonna try and solve this problem in practice, you actually need to meet practitioners sort of where they're at. Since then, there's been a lot of interest in the system. We've developed a certificate course at Florida State University to go and train practitioners in how to use this system. At this point in time, we've gone through 107 participants in that training program, and it's been a really interesting process to sort of educate non-machine learning experts on how to interpret these model outputs in practice. This is what our instruction focused on, mainly limitations of the models, the benefits that they can expect from the models, where the models will fall short, and when they do, what direction will they make errors in? Inference times and compute limitations. The practitioners are really concerned about being able to run on hardware in the wireless denied or limited environment, and so that was a big point for the training. Product formats, again, making sure that we have a good handle on the things that we're actually going to be delivering. Those CSVs, those GeoJSONs, PDFs and such. We had a little bit of time dedicated to how and when you should collect imagery for these models, specific to UAS flights. Fly at high noon to limit shadows and target sort of a 3 centimeter per pixel ground sampling distance. So the models we have now have the best chance of working in practice. And then points of contact, if you actually want to engage with us. We had a post questionnaire survey, a post training survey. And we had 43% say that this was before the hurricane season was over, but 43% say that they were interested in utilizing the system if there was a hurricane that hit during the 25 hurricane season. And 52 said maybe, only one said no. So we're taking that as a win. These people are not technical, so it's hard to say whether or not they would actually adopt this system, but at the very least they are, there's interest. And if you want to learn more about this deployment and about the training process, we have a paper coming out in IAAI AAAI in 26 later in a couple months. So let's quickly talk about some future work. This frequency-based stuff, we're actively training models on this. Again, if you've got thoughts, I'd love to chat. There's some really interesting stuff here. The second is this sort of quirk that we have. Some call it quirk. I think it's actually a feature, not a bug, which is that every source has its own label. This means that we can calibrate our models across scales. And so the function we're trying to learn is no longer like, what's the probability that we're right? but more what's the probability that if you send a better sensor there, you're going to get a different answer. So you've got this low resolution satellite imagery. Can we learn the function that says, hey, if you go to these buildings, we think you're going to get a different answer? So that would have some really interesting impacts in terms of how you deploy these systems in practice, where they get sent, and sort of, yeah, what that whole process looks like. I'm coming to the end here. I've got just two things I want to finish with. First, we're going to be hosting a symposium on the intersection of artificial intelligence and humanitarian assistance and disaster response. This is coming up in April in San Francisco. Dates are April 7 to 9. We're going to be the full CFP is not up, but if you go to hatter.ai, you will find the details for what we've got so far, and the full CFP, I think I can say, will be coming out tomorrow, at the very least Saturday. So we've got a pretty good organizing committee. I think we've got some good speakers lined up. A bunch of people from CAL FIRE are coming. So if you're interested in this discipline, in this area, please submit or attend or just follow up. So with that, I'll leave it. Just the things I want to hit you with. Cracer UDroids now is the largest multi-source data set. It's operationally valid. It's the only data set of its kind that controls for multi-source spatial misalignment and just multi-source imagery in general at this scale. We've just finished up the first deployment of drone damage assessment models in practice. We've got this practitioner training program. It gives us a really interesting sort of environment to engage with practitioners and also to think about what the next versions of model training looks like when we've got these humans in the loop. And then, we're actively in the process of training these cross-scale and cross-source computer vision models. So if you're interested, I'd love to chat, and I think I'll leave it at that.